A huge welcome to everyone. It's a pleasure for me to be teaching you about neural networks. So please pour your favorite drink and let's get started.
So we will start with this beautiful slide about neural networks. In fact, the rings doesn't mean anything, but okay, let's start. We're going to have two parts. One part in which we're going to talk about the simple concept. A second one to understand how the perceptron works, and then the forward propagation, how specifically the neural network is working. After that, we are going to have another video called part 2, in which we are going to talk about the back propagation, how it is trained, how are we fixing errors inside the neural network. Finally, how are we going to evaluate how the neural network is working. So imagine that there is a guy called Juan Felipito. That was my nickname when I was a little kid, Juan Felipito. And Juan Felipito is there. He's happy because we are using him as an example for this clip. His brain is in every moment of life by its interface, that is like, are we receiving signals, frequencies, images? That brain is obtaining songs, pictures, smelling things. So all type of possible signals are getting into Juan Felipito's brain. When the brain receives a signal, it processes this signal and it gives us a reaction, an attitude, a decision. So imagine that there is a specific type of food in the restaurant and Juan Felipito is there. He don't like that smell. So is the same process, a signal, a process inside the brain, and a result of that output. That is the same way the neural works. We have there in yellow entry or inputs to the neural networks. We have different hidden layers that are the ones blue and green. And finally, we got the last neuron. That is the one that is giving us the result, the last layer. Can we understand this, but applying to the specifically artificial intelligence models? It receives databases in forms of tables, in forms of pictures. In fact, it can receive movies. So there are a lot of types of inputs that our network can receive. It is going to make a different process. We are going to build this way to process the data. And finally, we are going to have a prediction or a classification based on those inputs. So let us talk about the simple item of all of this technology, all of this topic, that is the perceptron. It's simple, the basic unit of inference in the form of a linear discriminator. In other words, it is going to process some input, make a linear processing, and sending an output, a numeric, for example. If the inputs are numeric, we're going to have a numeric output. It's important in this moment for you to understand one of the most important concepts in the perceptron, that is the learning rate. The learning rate is a constant that determines the magnitude of the update that is applied to the perceptron weights after each training step. In other words, the learning rate is going to give us the jumps, how it is going to jump when it is updating the different weights and biases inside the perceptron. So let us take a look. This is the perceptron. This is the neuron, and it receives input, process something inside of it, give us an output. And what can we expect of this process? Like if we have one input called x1 and a second input called x2, our system or perceptron is going to process in linear form how to divide the rings and the cubes into different groups. So it is going to find that line that can split both groups. We can also have more inputs, not only 1, 2, we can have 3, and we are going to talk here in 3 dimensions. So it is going to be a plane, separate both type of inputs, in this case the rings and the cubes, and we are going to have a specific plane that can divide both categories. Can we have more than 3 inputs? We can have whatever kind of inputs that we want. In this moment, we cannot sketch more than 3 dimensions, but we can process in the perceptron more than 3 dimensions. So this is a sketch. Sorry, it is in Spanish, but I'm going to explain you in the most accurate form. We have 5 inputs. This is the standard diagram. So we have 5 different inputs with the respective weights. Here we are making the linear processing. After we make that formula, we have to apply to that result the activation function, and then we get the output. But what are those activation functions? We're going to talk about them in a moment. So here we have our perceptron. In this case, only 2 inputs, 2 weights, 1 bias, each in every construction of perceptrons. Each neuron, each perceptron has a bias. Each input, a weight. Good. And as I'm seeing here, it looks like the Namekusei. I don't know if in your country was a cultural comic, but in our countries, yes. And it looks like the Namekusei. Okay, no, Namekusei was a little bit more green. There we have. And we can call it Namekusei neuron, only to put like an interesting topic to the explanation. So we have here the neuron. The bias, the definition of the bias is an essential component because it allows the learning and the optimization process to be done. So if we don't have a bias, we are not going to allow the neuron to manage difficult problems, complex problems. We always apply a bias. Let's put some numeric values. Let's assume that we have a 4 in the second input, a 3 in the first input. The weight of the 3 of the first input is going to be -1, and the second weight from the second input is going to be 2. We have also a bias, -1. The process is going to be a linear process. 3 dot product -1 plus 4 dot product 2 plus -1. The result is 4. Do you think that the result of this perceptron is 4? No, because we need to apply the activation function. After the activation function, we will have the result of our enigma. The activation functions are these ones. It is simple but important to apply activation function in every neural network. As we are talking, the perceptron is the most basic unit of the neural network, and it introduces non-linearity into the calculations of each neuron. It allows the neural network to learn all the complex relationships between the input and the output. And without these functions, probably the neural network will be unable to work with complex problems. You know, the real world is not a linear world. So let's apply to our perceptron a heaviside. What is going to do? If there is a negative value, is going to be 0. If it is a positive value, is going to be 1. So in this case, as our result is 4, the result for all the perceptron is 1. Okay? Let's make a little problem, a simple, quite simple problem to understand fully the perceptron. Imagine that we have a VIP human club in which, depending on 2 variables, you are getting in or you are not getting in the club. First variable is if you like pizza or not, and the second is if you like dogs or not. Of course, if you like pizza and if you like dogs, you are going to be in the club. But we have different results. If you don't like one, if you don't like both, you are not going to be in the club. So we can model this in a perceptron in a quite simple way. So let's put aleatory 2 random values as weights and 1 random value for the bias. So the first scenario is 1 in variable 1, 1 in variable 2. So we process all of this, we process the linear formula, and we obtain that the result before the activation function is -2.5. After the heaviside, after the activation function, we get that it is 0. Okay, good. We always have to put what we expect and what we are getting with the perceptron. So in this case, the expected value was 1 and we are getting 0. So here we have an error. There we have to apply the update functions. So update function number 1 is how to change the weights. We apply the learning rate. This Greek letter is going to be the learning rate, and it's a value that we can establish as we want. Commonly, we use 1, and then we apply the different formulas and get a result. We have to make this is called experiments, how you make different experiments to get the best hyperparameters. That is a thing that you can find in my other clips, where I make all of this, but in a script, because making this type of experiments by hand, okay, is impossible. So we decide that in this case, the learning rate is going to be 1. Y minus y with the hat, the difference between what it must be and what we are getting. And we apply the dot product with the input. Also, we have to update the bias, and is the learning rate dot product the error. So in this case, we got an error of 1. We get a scare alert. So we apply the different formulas. So in this case, the only processing here is putting the numbers in their respective formula for the weight 1, weight 2, bias. And we change the values in the formula, in the perceptron. And then we get again into the problem. So with the second scenario, we don't get any error. So weights and bias are okay. But in the third one, there is an error. We have to update again. Okay, no. First, we get a scare, and then we update. So weight 1, new weight 1, new weight 2, new bias. And after we apply this formula until we get 0 errors, we found that in this case, the problem is deleting, not taking into account the second input, because anything dot product by 0 is 0. So in this case, one of the possible results is we get W1, the weight 1 is 1, W2 is 0, the bias is 0, and we get the result. It is going to be a long talk to decide if the weights are fine or not, because in this case we are deleting what variable. So it depends on the problem. What we can change there, for example, the learning rate, not being 1, being probably 0.5, being 100. We have there to apply the experiment and to understand if the result is resolving our specific problem. The perceptron can receive a lot of W's, lot of inputs. Remember, only one bias. But is the perceptron ready, one perceptron ready to resolve all issues? We don't know. This is you can make this with a perceptron. We can play to resolve these are the logic gates. And for example, it can be a good experiment. How can you manage your weights and bias to get the AND gate or the NAND? Can you resolve this with one perceptron? For example, the SOAR commonly needs more than one perceptron. So this can be a good way to fully understand the perceptron. In this video, we use a problem that I just invented. The idea was for you to understand that in the neural networks, we are using the same idea. Yes, we are using the same idea of we have weights, we have bias, we need to process linear mathematics, and then we have to apply an activation function that is going to give us a result. Take a look on this screen. How many weights do we have? How many biases do we have there? So imagine the amount of calculation that we will have to do. It's incredible. Only put the W's, the weights, in the first connection between the input and the first hidden layer. but we have from the first hidden layer to the second. So there are a lot of values that are going to be involved in this problem. So to understand how the neural workings are actually working, I'm going to use a completely incredible example. If you are not understanding these photos, you can first cry a lot, second, send me a pizza, and third, watch the movies. I'm going to explain you the example that we are going to use. Imagine that there is Frodo and Sam from the Lord of the Rings, and this is the sword. I don't remember the name of the sword in English. When an enemy is getting closer, it puts blue, and if is not an enemy, it remains the same color, the common color. So the idea in this example is, we are going to tell the sword A, you don't need elfic magic, you need a neural network. And we're going to apply the neural network to the sword. So in this case, the idea is, if there is a human or a thing with specific meters of weight, for example, if there is a friend that is getting closer, it is going to remain the same. And if there is an enemy, it's going to put blue. Simple. So how is going to work this? We have two neurons. Yes, we have one variable that is going to be in meters and the respective weights and biases. So remember, we have to achieve this curve. So imagine that we put a random weights and biases, and we introduce our first value. So what is going to happen? It's going to apply the formula, the linear formula, with the first path, and the same formula with the second path. We are getting a value. We are using the ReLU activation function. We watch it in the sheet of activation functions. What it's going to do is, if there is a negative value, it's going to be 0. And if it is a positive value, it's going to be the value. Okay? So in this case, the result of the first path is minus 0.3. And the second one is 0.4. So the result in the first path is 0. Below path is going to be 0.4. Good. So we have to graph it. Remember how is the result in the curve that we need as the result. Remember, the x edge is going to be meters. If we try with 1 meter, if the person that is getting closer 1 meter of height, this is the result. With 1.8, 2 meters, 2.5, 3. So as you can see, we are building using dots, we are building curves, and the result is we have one blue, okay, both are blue. We have one blue curve and other blue-green curve. We cannot only have this result because we need to close our neural network. So we apply the last two weights, and you can answer me this. Does the final perceptron neuron has a bias? Yes. The input layer, you are not going to put biases, but from there to the end, you have to put biases. So in this case, we put W3, W4, and the bias. I put 4 because of yes, and 1.7 as weights, and the bias -1. Perfect. So what is going to happen there? The result of the activation function is going to be dot product 4 above, and below is going to be 1.7. It is going there. When you apply the dot product, you have to sum both values and then apply the bias. So how we can apply this? Here we have only until we apply the ReLU activation function. When we apply the W3 and the W4, we obtain this one, W3, W4, and sum both curves, we obtain this green one. And the last, the bias, is going to help us to get more of accuracy in terms of the complexity of the problem. In this case, what is going to be that -1 is moving below a little bit our final curve. So here we have the result of our neural network with random values in weights and biases. What do you think about this? What I think is that we are not going to have any Frodo and Sam because the orc is going to kill them. Eat them. When there is when we have low meters, it is not going to apply the blue sword. Like when it is in the middle, it is going to be blue. And quite at the left is going to be the same color of the sword. And in this case, it is switch. We need the purple one and we are getting the green one. So what do you think about this? We will have to make the process from the perceptron to modify the weights and the biases. And this is called the back propagation. This is the process that we are going to watch in the second part. But in this first part, the important thing is you now know how each neuron is working. And how are we going to change and to make an accurate neural network is going to be in part 2. If you want to engage with my content, there you have on my social networks. Also, you can write to me whatever you need. My objective is to democratize this knowledge and to make you be happy knowing these respectful and huge new technologies that is important for all of us to know how to apply.